length of a path, did we define? We defined as a supremum. But the geodesic is the one which takes infimum among all the paths. This we didn't write. So geodesic is actually defined to be gamma geodesic. This has also questions, so I have to state. If we take the infimum of the length, gamma geodesic connecting EV, for example. Gamma path. Then this gamma which takes the infimum is called geodesic. And you have to know that in this case, the infimum may not be attained. It can or cannot be. It doesn't need to be attained. There are examples, of course. Usually, write down some typical examples. Now we are going to move one more definition. One more definition.
So for a geodesic space, it will always be attained infimum.
Yes, if it is
Geodesic space.
yeah, if geodesic equal to infimum, yes. For geodesic space, it will be infimum. So the geodesic space is simply defined by the infimum is K. And if there is a if the distance function rho is intrinsic, then we call the space, this name is seldom used by me, call the space length space. Another definition. It's all in the slide, so I will not write the full definition. If the distance function is intrinsic in X, then X is called length space. What are good examples of length spaces? Of course, those are. Those are also length spaces. Now we come to another definition. Before defining this, we need to chat a little bit. The chat is about this. Topology, the whole course of topology was began as study of two things, actually. Careful study of two things. What are they? They are very interesting questions, and I did give a talk on several years ago on the SIMPA about that. If you have listened to that, you know the answer. Topology began the earliest topic, two topics which topology seriously studied was one is dimension. I will a little bit expand on this. One is dimension, the other one is called what is curve. What is a curve? And we have defined the curve in this way. This is actually not very good definition as well. This is a piano definition actually. This definition of a curve or path in a metric space, which is not good enough. You have to know that this probability is high and this definition must be adopted. It is one definition here we can use, but it is not the best. So the early study of topology was dimension of a space and what is meant by curve, which led to amazing discovery which were not known before that time. Mainly related to the names of Poincaré and several other people. First of all, you see, if you define a dimension, you see, in linear algebra, we define what is the dimension of a vector space. It was defined very algebraically and nicely. It is a number of vectors in a smallest generating set,
Yes.
or the number of vectors in a largest linearly independent set.
Independent set. Yeah.
And the two are equal in if the space has a dimension. And then you can actually define it nicely, another linear algebraic definition of a vector space. But you know that in topology there are lots of, most spaces are not vector spaces, right?
Yes.
So how did, for example, a space like this, how do we see that our intuition tells us that these are dimension 2, if it is only in the Euclidean plane. But how do we define the dimension using only the open set, which is the topological definition? How do we define a dimension of a topological space only using conceptual topology? This question you should consider, and of course it's all done. But there is a definition given by Lebesgue, called the Lebesgue dimension, which was given by in terms of open coverings and their overlap number. And then from all open coverings, you choose the overlap number smallest, and that number plus 1 is the dimension of this topological space. But you know that there are lots of other dimensions, I think. You at least know, especially those people who do fractals. Lebesgue dimension, because being it's an overlap number means it's a positive, non-negative integer. Non-negative. But there are different dimensions which are not necessarily integers, right? I think some of you told me that you are doing fractal. The fractal's Hausdorff dimension is not necessarily an integer. That is also a topologically invariant, no problem. But something which is equivalent to Lebesgue's dimension, or if you evaluate it, you get the equal number of the Lebesgue dimension. That would be more interesting because that is completely from within pure topology, without applications or iterations and things like that. So dimension is the number one thing. Second one is curve. More precisely speaking, when we were first studying calculus, we were told by our lecturers that the number of independent variables in a function. What does it mean? What does it mean? Number of independent variables in a function is supposed to be the dimension of the graph, of the function. Graph means it's image. Image space has the dimension which is given by the number of independent variables. But the number of independent variables was actually completely ridiculous concept. Why? Have you ever heard of Piano and Hilbert space-filling curves? I have lots of nice diagrams on the slides of that. For example, if you start with a rectangle or a square, and then first probably break one side and put it, I forgot, I have a nice drawing in the slide, so I'll show you later. There exists a continuous mapping from 0, 1 into to the square. This was what Piano proved. Continuous mapping. So you can stress this line segment of fixed length so that you can fill this area. And the proof is not difficult because it is done by something like that. Then you bring all of them. I will show you later using my slides. As soon as this is done, you can actually map 0, 1 interval continuously into the cube of any size. And cube of any size, especially if you take the boundary out, which is homomorphic to the whole space. So which means that you have a line segment of fixed length which which is continuously mapped into Euclidean any space of any dimension. So now, what is line segment has dimension 1, according to the original understanding, it has one independent variable. But the Euclidean dimension, the space of dimension n has dimension n. So dimension doesn't seem to be an invariant under continuous mapping. That was what Hilbert and Piano first and Hilbert observed. After that, they made it more rigorous, so that we do now have a good understanding of dimensions of a topological space. Because topological space is the most general space if you want to go slightly above set theory. If you land on set theory, there's nothing there, no dimension there. So if you try to just get any positive distance above set theory, you enter topology, right? It's a gut feeling, the direct intuition. So for topology, we need to really carefully define what is meant by dimension, what is meant by curve. So that was the earlier study. Now, we are not talking about only topological spaces in this course. We are talking about metric spaces. And metric spaces, dimension can be given by topological dimension, a big dimension, no problem. But that relies on open sets and covering. So there was a consideration about this question in 1953, and there is actually a whole monograph on it. It's called metric dimension, and there must be 100 people in Pakistan who are studying metric dimension of graph, finite undirected simple graph, especially the special family, paths, cycles, and so on. You shouldn't really do that, but and then every one of those papers, I read many of them, usually cite 1976 Harari and Bell-Kerr paper. That's the first definition where metric dimension concept was given. But it wasn't. It was actually given by Blumenthal. "20 years earlier than Harari and Bell. So we should really cite him if we are citing. But every graph theorist only cites papers from other people's papers, so they don't even check. You shouldn't do that if you are writing papers in metric dimensions of graphs. You should really cite Blumenthal topology. So, and in that paper, metric dimension of a metric space was given, which means it includes all those spaces plus graphs. So let's give you a metric space. And I'm not going to cite it, it's all well known in Pakistan. You should check those papers in. I'm going to define my own, which is generalized dimension, which covers the original metric dimension. It's a special case, and partition dimension studied by many people in this Salam-SMS as another special case. So I'm going to define it in general. This ought to have been given earlier, but Blumenthal didn't give. Blumenthal gave the ordinary metric dimension definition of an ordinary metric. Now let's
You want it today or maybe next time?
Sorry?
You want to define that today or maybe next time?
Today we take only 5 minutes.
Then okay.
Is that tolerable? It's Monday, not Friday.
Yes. That's why you're saying Monday is tough. We have just woke up. We'll get better on Wednesday.
Yes, okay. So we will start from this on Wednesday. We have chatted too much. The chatting is important because
Yes,
you have to know that where topology started, and nobody now teaches topology, tells you that. I don't know why.
nobody teaches us topology nowadays.
I will teach you topology. I taught topology many years.
Okay. So we should arrange another class?
Eh?
Another class in the week?
Next year, you in a week is fine. Because I think I can manage 2 courses. I can give a very good topology. It's all ready because I have slides, exercises, answers, exam test questions. Taught it many years, so it's all ready. You can't let me teach topology or in group theory. So topological study of topological spaces began with the dimension and independent variables in the curve. Any questions and comments? You are a good student. I think you should try to do some of these questions.
Yes.
I encourage you.
Thank you for the compliment.
It is a statement of fact.
This is a very foundational.
It's very low. They're very basic, yes.
But they are like much harder at the same time.
When it is closer to septum, everything becomes hard.
Any questions?
Ladies,
Ladies and gentlemen.
don't be shy.
Thank you so much.